Srimati R. Padmavati, Head of Department EC, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, Oscillators and Amplifiers. In this module, we are going to discuss about the log amplifiers, anti-log amplifiers and sample and hold circuit. The log amplifier, one of the most useful circuit techniques using log amp is logarithmic and anti-logarithmic amplifiers, which are non-linear circuits. It converts a linear voltage or current into corresponding logarithmic value. It is well known that some of the functions such as multiplication and division can be performed by addition and subtraction in log scale. The numerous applications in electronics such as dynamic range compression, raising to powers, taking roots, RMS conversion and multiplier and divider circuits. Now, we are going to deeply discuss about log amplifier. It is an amplifier for which the output voltage V out is k times the natural log of the input voltage V in. This can be expressed as this equation V out is equal to minus k T by Q, natural logarithmic of V input voltage divided by R1 Is, where Is is the saturation current, Q is the charge of the electron and K is Boltzmann constant, T is absolute temperature and Vt is the thermal voltage. So, these are the circuits of log amplifier. When you see the amplifier circuit, log amplifier circuit, in the first circuit in the feedback, diode is present. So, we can use the diode in the feedback circuit for log amplifier, otherwise we can use a transistor instead of diode in the feedback circuit of the log amplifier. So, here if you see the transistor, the base terminal of the transistor is grounded and the collector terminal of the transistor is also virtually grounded. So, these two terminals, base and the collector terminals, are in same potential and this transistor is now acting as a diode. So, this can be discussed now, this circuit. So, here the input voltage is given to the negative terminal of the operational amplifier through the resistance R1 and some part of the output is fed back to the same negative terminal of the op amp through the diode connected transistor and the positive terminal is grounded here. So, from the circuit already see the output is derived as minus kT by Q natural logarithm of V in divided by R1 into Rs. This is going to be derived from this circuit. So, since this transistor is a diode connected transistor, we are going to have the equation for the current is given as emitter current is given as the saturation current into e power. So, the emitter current of the transistor is given as IE is equal to the saturation current into e power kT by Q minus 1. So, here this emitter current is also equivalent to the collector current. So, I can replace this emitter current as IC is equal to the saturation current e power kT by Q minus 1. So, now IC by Is is equal to e power kT by Q minus 1. And if you take natural logarithm, this exponential term will be neglected. So, it will be kT by Q is equal to natural logarithm of IC by Is, and about this 1, this will be neglected when you compare it with this term totally. So, after this equation, when you compare it with the IC by Is, because this saturation current is 10 power minus 13. So, this term will be very high and so this 1 will be neglected and the final equation will be kT by q is equal to natural logarithm of IC by IS. When you see the equation, it is kT by q natural logarithm of V in by R1 into IS. When you simplify this equation, you will be getting what is IC current in the circuit. It is the current flowing through the resistor R, that is the input resistor R. So, we can replace this as Vi by R1, and if you substitute in that equation, you will be getting V out is equal to, and what is this V out is the emitter voltage of the transistor. So, V out will be the emitter voltage of the transistor, and now it is V out is equal to minus kT by q natural logarithm of, and instead of IC, if you put this Vi by R1, you will be getting Vi into Is R1, and if this Is R1 is taken as V reference, the final equation will be V out is equal to minus kT by q natural logarithm of Vi by V reference. So, what is the disadvantage of this log amplifier without the compensation technique is this temperature. If the temperature increases, then the saturation current of the transistor will also get changed. So, we have to compensate this parameter. So, we are going for the compensation circuit as we are giving the V reference separately in another operational amplifier circuit, and here Vi is given to R1, and here a diode connected transistor, base is grounded, and this emitter is connected to the output. And if you give another operational amplifier or a log amplifier circuit for the reference voltage through the resistance R1, here you are giving a reference voltage V reference. So, take this as V1 and this as V2, and now these two voltages are given to a differential amplifier circuit. Keep these resistances all are having a same value of R. So, this is a differential amplifier circuit, and finally an non-inverting amplifier. So, here RTC, this is a, you can take this resistance as a transducer type of resistance. When the temperature changes, this resistance value will also get changed. So, this has a positive temperature coefficient. So, when the temperature changes, it will also getting changed. So, with this circuit, this is a temperature compensated circuit. Here the reference voltage is given in another logarithmic amplifier, and input voltage is given in another logarithmic amplifier. When you calculate this V1 and V2, and if this is given to the differential amplifier circuit, you will be getting V2 minus V1, and finally, if it is given to the non-inverting amplifier, and this is considered as R2. So, after this, the voltage will be compensated voltage. So, this will be finally given as compensated voltage is equal to kT by q natural logarithm of V naught by V reference into the gain of the non-inverting amplifier. So, what is the gain of the non-inverting amplifier? It is 1 plus RTC by 2, since RTC is the feedback resistance here and R2 is the input resistance here. So, when you calculate, when you recall, the gain of the non-inverting amplifier is 1 plus RF by RI, where RF is the feedback resistance and RI is the input resistance. So, instead of the feedback resistance, we are giving here RTC. So, this is a temperature compensated resistor here. So, whenever the temperature is getting changed, this resistance value will also get changed accordingly, and so the effect of the temperature it will be compensated by this circuit. And why we are giving a V reference in a separate circuit is 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 the saturation current. The IS saturation current is also getting decreased or increased based on the changes in the temperature. So, we are considering that the operational amplifier, both operational amplifier having same IS close to matched between the same saturation current with these two logarithmic amplifiers. And so, the reference voltage is given separately here, and finally, the output of the logarithmic amplifier is temperature compensated. And again, one more disadvantage in this circuit also, because we are using lot of 4 number of operational amplifiers here. So, we can compensate the temperature effect with the 2 number of logarithmic amplifier. The emitter current is given as IE is equal to the saturation current into e power VE Q by kT minus 1. So, the emitter current is equivalent to the collector current in this circuit. So, IE is equal to IC e power VE Q by kT minus 1. So, we have seen all these parameters in the previous slide. So, this is again rewritten as IC is equal to IS e power VEQ by kT minus 1. Again, if this 1 comes here, so IC by IS minus 1. When you compare with this IC with 1, so this IC by IS is very high. So, this 1 is neglected after this equation. And now, if I take natural logarithm for this equation, this exponential term will be go away. So, you will be getting VEQ by kT is equal to natural logarithm of IC by IS. And what is this VE in the circuit is? It is minus V naught. And what is this IC in the circuit? It is VI by R1. So, substitute both in this equation, you will be getting V out is equal to minus, if you take these terms kT by Q in that side. So, it is kT by Q natural logarithm of this IC, instead of this IC VI by R1 into IS. So, this R1 IS can be referred as V reference voltage. So, what is the disadvantage in this circuit is this temperature. If this temperature changes, then this saturation current of the transistor will also get changed. So, we have to compensate this, we have to maintain this saturation current, so that the reference voltage will also be maintained. So, this is the final equation of the log amplifier circuit. V out is equal to minus kT by Q natural logarithm of Vi by R1 IS. So, now we are going to compensate this temperature changes in the circuit with the next circuit. So, here we have 4 number of operational amplifiers. The first 2 operational amplifier will act as log amplifier. So, in the first amplifier we are giving the input signal, in the next amplifier we are giving the reference voltage. So, now the reference voltage is kept constant and the saturation current is assumed to be similar, closely matched with these 2 operational amplifiers and transistors. So, V1 is the output of this logarithmic amplifier, first amplifier A1, and V2 is the output of the second logarithmic amplifier A2. So, we know that what is the output of V1? V1 is minus kT by Q natural logarithm of Vi by R1 IS, we have derived in the previous slide. And what is V2? The output of the second logarithmic amplifier. So, here instead of the input signal, we have given the reference voltage. So, what is the output here? It is V2 is equal to minus kT by Q into natural logarithm of this V reference by R1 into the saturation current. So, we are considering that the saturation current of both the transistors are closely matched. So, IS1 is equal to IS2. So, we can say this as IS commonly. And now we have got what is V1 and V2. So, these 2 voltages are given to the differential amplifier, and considering all the resistances of the differential amplifier as equal. So, you will be getting the output of the differential amplifier here as V2 minus V1, as V2 minus V1. So, next the VD, the difference in voltage will be given to the non-inverting terminal of the operational amplifier. The inverting terminal is simply grounded through the resistance R2. So, this has the feedback resistance as temperature compensated resistor. So, here if the temperature changes, then the resistor value will also get changed, and so the effect produced by the temperature will be nullified by this resistance RTC. So, here this voltage is given to the non-inverting terminal of the op amp, and the output, the voltage compensated voltage will be obtained as the gain of the amplifier with the input voltage of the amplifier here. So, it is derived as the gain A into kT by Q natural logarithm of V naught by V reference. We will be having a negative sign here. So, what is the gain is 1 plus RTC by R2. This RTC presents in the feedback loop of the operational amplifier, and this is the input resistance of the operational amplifier. So, when you recall the gain of the amplifier as 1 plus RF by R2, similar way here 1 plus RTC by R2. So, this is the gain which is multiplied with the difference in voltage of the logarithmic amplifiers. So, here kT by Q natural logarithm of V naught by V reference, where A is 1 plus RTC by R2. So, again there is a disadvantage in this temperature compensated circuit. What is that is, we have used 4 number of operational amplifiers. We can use 2 number of operational amplifiers with the temperature compensated resistor for the avoiding the effect made by the temperature. Now, we can have a break. Welcome back after the break. So, previously we have seen log amplifier, and now we are going to discuss about the anti-log amplifier. So, in the circuit, if you compare it with the log amplifier, this circuit has reversed connection. So, here in the input side the diode is present, and in the feedback side resistance is present. If you recall the log amplifier, in the input side we have a resistor, and the feedback we have a diode. Here it is just reversed. So, we are going to discuss with the diode connected transistor in the input side, and here there is a resistance in the feedback side. We are going to discuss about this circuit particularly. So, here this is the output of this circuit has the anti-logarithmic value of the input resistance. Now, whatever the input voltage is given, the output will calculate the anti-logarithmic value of the input. So, but again we have a saturation current which is dependent on the changes in the temperature. So, we have to go with the compensated circuit for this anti-log amplifier also. So, we are going to have only 2 operational amplifier circuits here. Always the positive terminal is grounded, and always to the negative terminal we are giving the input signal, and this is the diode connected transistor, and here the input to the circuit is the output of the circuit of this is same as the input, output is same as the input here. Consider this is R1, and again another amplifier which is all these 2 amplifiers are acting as a logarithmic amplifier now, and again this resistance is R1, this is grounded. Here we are giving constant reference voltage like what we have given in the temperature compensated logarithmic amplifier. In the same way we are giving the reference voltage separately to the logarithmic amplifier here. Again in the feedback there is a diode connected transistor, say this is Q1, this is Q2, this emitter is connected to this emitter, and also it is connected to the output of this second operational amplifier, take this as A1, A2, and here this base is connected to the input voltage through a resistance R2, and here we are having the temperature compensated resistor. So, to the base of this transistor Q2 we are giving the signal Vi through the dividers R2 and RTC. So, this is the temperature compensated anti-logarithmic amplifiers with only 2 operational amplifiers, but previously we have seen 4 operational amplifiers for compensating the temperature changes for the logarithmic amplifier. So, I have already said that it can be made as 2 operational amplifiers for the same effect. So, here in the anti-logarithmic amplifier I have given the circuit for the temperature compensation. So, for operational amplifier A2 is getting the reference voltage, constant reference voltage, and A1 is getting the part of the output voltage V0, and the base of the transistor Q1 is connected to the base of the transistor Q2 and to the output of A2, and this output is given back to the input of A1, and here the base of the transistor Q2 is given the input signal through the resistors R2 and RTC. So, the main part is RTC here. So, now we are going to derive the output of the circuit. So, consider this as VA and this as VB. Okay. So, here what is VBE Q1? We have derived already the output of the logarithmic amplifier as kT by Q natural logarithm of input voltage. Here for the operational amplifier A1, the input voltage is V0 by R1 into Is. Here also the saturation current of the transistor Q1 and Q2 is closely matched. So, I have given commonly as Is. And what is VBE Q2? It is again kT by Q natural logarithm of the input voltage of this particular circuit A2 is V reference. So, I am giving it as V reference by R1, the same resistance used here, and Is. And what is VA? VA is the reverse of the base emitter voltage of Q1. So, it is the reverse of the base emitter voltage of Q1. So, it is minus kT by Q natural logarithm of V0 by R1 into Is. And what is VB? VB is the voltage V1 is given through the dividers, potential dividers, and it is given to VB. So, this is nothing but the voltage across the resistance RTC. So, how will you calculate this voltage? By using the potential divider rule. So, VB is calculated as the input voltage into the opposite resistance divided by the total resistance. This is VB. Now, we are going to calculate the emitter voltage of the transistor Q2, right. So, what we have given these equations. So, here VBE of Q1 it is kT by Q natural logarithm of input voltage of that amplifier A1 divided by R1 Is. So, why there is no negative sign here is VBE, always we are calculating VBE in this circuit. So, but we have taken this the base is grounded here, the emitter is here. So, we are calculating the voltage VBE, but the output voltage if you calculate it as from this terminal. So, it is reversed. So, we are removing this negative sign. So, similarly for the transistor Q2 also VBE is from base to emitter, but always we will calculate the output voltage from this terminal, output of A1. In the logarithmic amplifier, when you recall it, the output is connected to the emitter terminal of the transistor. So, we will be reversing the voltage, that is what the negative sign is neglected here, or negative into negative you will be getting positive sign. And what is the voltage VA? VA is the voltage at the emitter. So, I am reversing what is we have calculated from the base emitter base voltage. So, it is minus kT by Q natural logarithm of V0 by R1 Is. And what is VB? It is the voltage across the transistor compensated resistor. So, using the potential divider rule we have calculated this, and now we are going to calculate the voltage at this emitter of Q2. Emitter voltage at Q2 is given as, from the circuit, how can you give the emitter voltage at Q2? At this point, it is the voltage from the emitter to base of Q2 plus the voltage at this point, that is VB. So, I can write it as VE of Q2 is written as VB plus VEB of Q2, right. So, VB is calculated as VI into RTC by R2 plus RTC plus, what is this VEB of Q2? You have to reverse the base emitter voltage of Q2 here. So, it is minus KT by Q natural logarithm of V reference by R1 into IS. What is this VEQ2 when you see the circuit? What is this VEQ2? It is nothing but this voltage VA. So, you can replace VEQ2 by VA, and what is VA? We have calculated here. It is minus KTQ natural by Q natural logarithm of V naught by R1 IS. So, I am just replacing this VEQ2 as VA and substituting what is the value we have calculated for VA, minus KT by Q natural logarithm of V naught by R1 into IS is equal to the same part you will be getting here. So, after simplifying, so here you have to commonly take this KT by Q out, and finally, you have to calculate from this equation what is V naught. V naught is finally calculated as V reference into 10 power minus K dash V I. So, this is what the output of the temperature compensated anti-logarithmic amplifier. Okay. So, when you change 1 volt in this input voltage, when you change 1 volt in this input voltage Vi, then the output voltage will be getting changed or decreased by 1 decade. Okay. So, that is the output we are getting from the anti-log amplifier, and we have to know that how the natural logarithmic value will be converted into logarithmic value. So, when you multiply 0.4343 into the natural logarithmic of, say for example, A, then it will be giving log to the base 10 of A. So, this is the conversion factor. When you multiply the natural logarithmic value of any value with the 0.4343, you will be getting log to the base 10 of that particular value. So, after substituting these here in this calculation only, we are getting the output V naught is equal to V reference into 10 power minus K dash Vi, where K dash this RTC divided by R2 plus RTC into KT by Q, everything will come here in K dash. So, when you increase 1 volt in the input voltage, then the output will be decreased by 1 decade. So, this is what we are getting in anti-logarithmic amplifier. The next is sample and hold circuit. So, this is the circuit of the sample and hold device, and here the input is given to voltage follower circuit, and here instead of switch, here we are using a MOSFET, and there is a capacitor across it, and out of the output of the capacitor or the capacitor voltage is given to the voltage follower again, and you are getting the output here. So, instead of this 2 switches, assume that there is a MOSFET, and MOSFET is acting as a switch. Also, you can use these 2 switches, but you have to control both these switches here. If you use a MOSFET here, MOSFET is acting as a switch, we know that, and to the drain of the MOSFET we are giving a control voltage, and if the control voltage is positive the MOSFET is on, if the control voltage is negative the MOSFET is off. If MOSFET is on by using the positive pulse to the control voltage given to the drain, then the input signal is sampled and it is held across this capacitor, and whenever the MOSFET is off, the last sampled value is stored across the capacitor. It cannot be discharged through the operational amplifier, because we know that for the voltage follower the input impedance is very tremendously high. So, during the off period of the MOSFET, the capacitor holds the last sampled value, and if the MOSFET is again on by the control voltage, then the capacitor will again charge towards the input voltages given, and the same is given in the waveform. So, if this is the input voltage and this is the control voltage given to the MOSFET, and if the control voltage is positive the input voltage is sampled. So, this is the voltage across the capacitance here, and if the control voltage is positive the input voltage is charged towards the capacitor charged towards the input voltage, and if the control voltage is negative the last sampled value is maintained until the positive pulse is given to the drain of the MOSFET, and if for the next positive pulse the capacitor discharges or charges towards the input voltage. Here the input voltage is negative, and so the capacitor voltage samples the input voltage, and for the next negative pulse it holds the last sampled value. So, this is the way it is sampling and holding the input voltages. So, now the summary. So, we have seen the log amplifier, anti-log amplifier with the basic circuits and the circuit for the temperature compensation, and we have seen the sample and hold circuit. Questions: list the applications of log and anti-log amplifiers. What is the effect of the temperature on log and anti-log amplifiers and how is it eliminated? Define the sample period and define the hold period. These are the references. Thank you.